October 7, 2025. The European Space Agency drops the first official images of 3I/Atlas, the interstellar comet skimming past Mars. The world expects awe-inspiring detail. What erupts instead is outrage, a blurry dot, silence from NASA, China, and the UAE, and no sign of the sharp data everyone anticipated. Why did the most watched flyby in years, the Mars flyby that broke the internet, deliver only questions, and what are agencies hiding behind technical excuses? When backyard astronomers produce sharper images than billion-dollar missions and rumors of impossible chemistry start swirling, only one thing is certain: the real story is just beginning. So what are we not being told? At 9:22 UTC on October 7th, the first official ESA images of 3I/ATLAS dropped across agency channels. Within minutes, the world's biggest science accounts, space enthusiasts, and even meme pages blasted out the same underwhelming frame: a faint, blurry dot, barely brighter than the digital noise around it. By noon, ESA CASIS trended in 4 languages. Hashtags like #FuzzyDot and #WhereAreThePics surged across X and Reddit, with armchair analysts dissecting every pixel. The outrage didn't stop at disappointment. Side-by-side comparisons flooded in, showing backyard telescope captures with more apparent detail than the billion-euro Mars orbiter. Comments accused ESA of hiding something, pointing to the simultaneous silence from NASA, China, and the UAE. With every unanswered question, the pressure for a real explanation only grew. The KSSIS camera aboard the ExoMars Trace Gas Orbiter was never meant to chase interstellar visitors. Its job is to map the Martian surface in sharp color, tracing landslides and searching for subtle changes in dust and frost. When pointed at 3I/Atlas, 30 million kilometers away, the design becomes a limitation. Each pixel on CASIS covers about 340 kilometers at that distance, enough to swallow entire Martian volcanoes, let alone a comet nucleus that might be only a few dozen kilometers wide. The camera's resolution, 11.36 microradians per pixel, sets a hard limit. No matter how perfect the focus or how long the exposure, anything smaller than a pixel becomes a blur, its light smeared across the sensor. Nick Thomas, the principal investigator, called it a stretch even to get a detection. The comet was at least 10,000 times fainter than the surface features CASIS was built to image. The team stacked exposures, tuned the tracking, and squeezed every bit of signal from the noise. The result, a fuzzy dot, was not a cover-up, but a technical ceiling. The coma, a cloud of gas and dust thousands of kilometers wide, blends into the background, while the nucleus itself is lost entirely. The physics is unyielding. At these distances, even the best hardware on Mars can only confirm the comet's presence, not reveal its secrets. The public wanted a portrait, the camera could only give a fingerprint. The next hope for detail would have to come from a different instrument, or a different orbit altogether. HiRISE, the high-resolution camera aboard NASA's Mars Reconnaissance Orbiter, was supposed to be the ace up Mars's sleeve. Its optics can map rover tracks from orbit, and at 30 million kilometers, it promised at least a glimpse, maybe a few pixels, of 3I/Atlas's core. But as the flyby unfolded, HiRISE went dark. The US government shutdown, which began October 1st, froze the entire chain. No command uplinks, no status logs, no public data releases. The official channels fell silent. For days, amateur astronomers and professionals alike hit refresh on the HiRISE archive, waiting for any sign of the campaign. Nothing appeared. Even the planning files, normally posted in advance, were missing. With NASA's feeds frozen, speculation turned to Mars's other eyes. China's Tianwen-1 orbiter and the UAE's HOPE mission had both tracked the comet's approach. Yet neither released images, statements, or even a denial. The silence deepened. Some pointed to the shutdown as the obvious culprit, but others questioned why 3 space agencies on 2 continents would all go quiet. In the absence of data, rumors filled the gap. Every hour without an answer drew more attention to what was missing. Not just a sharper image, but the sense that the world's best cameras were being muzzled. HiRISE's absence became the story. The missing crown jewel left the internet hungry for outside evidence, and every unanswered question fed the suspicion that something was being kept from view. In the hours after the European Space Agency's blurry dot went viral, the image wars began. Amateur astronomers from Italy to Japan posted their own versions, some with deep stacks of dozens of frames, others with AI upscaling filters promising to reveal hidden structure. By October 9th, the internet had split into two camps. One group claimed to see a sharp core, maybe even a hint of a tail or jet, arguing that backyard telescopes had outperformed a billion-euro orbiter. The other warned that every new detail was an illusion, a ghost born from over-processing and wishful thinking. Maya Trin, a well-known comet hunter from Melbourne, became the unofficial voice of the first camp. She published a sequence of images, each more processed than the last, with annotations pointing to what she called non-random streaks around the nucleus. Her posts racked up tens of thousands of shares, fueling a wave of speculation about what the pros were missing or hiding. But professional astronomers pushed back, posting side-by-side comparisons and running simulations. They showed how stacking faint frames can amplify background noise, turning cosmic rays and hot pixels into false structure. AI upscaling, they argued, only made the artifacts sharper, not the science better. The debate turned technical fast. Terms like sigma clipping, deconvolution, and pareidolia trended on forums as users tried to reverse engineer the truth from raw data. Some pointed out that even a perfect stack, at Cassis's 340 km per pixel scale, could never resolve a comet nucleus a fraction that size. The sharpest amateur images, when traced back, often relied on aggressive enhancement that introduced more questions than answers. With every new processed frame, the line between discovery and illusion blurred. The internet's hunger for detail outpaced what the data could honestly provide, and the call for rigorous, transparent analysis grew louder. If there was something to see, it would take more than software tricks to prove it. Anonymous posts began to circulate before the first ESA frames finished trending. As the rumor ecosystem expanded, so did demands for real data. The internet's appetite for answers now hinged on the next round of measurable facts: trajectory math, radio signals, anything that could be tested. Until then, the burden of proof stayed with the claimants, not the skeptics. Mallory Lefferland, Perseverance's shift lead, faced a problem that didn't fit the mission checklist. The rover's navcam wasn't built to chase comets, let alone one racing past Mars at nearly 90 kilometers per second. But on October 7th, she authorized a special sequence, 10 minutes of continuous sky exposures, hoping to catch a trace of 3I/Atlas as it tore through Jezero's field of view. The raw frames showed a single faint streak. It measured just over a pixel wide, stretching diagonally across the image. On first glance, it looked like a digital glitch or a cosmic ray, but the timing matched the comet's predicted pass to within seconds. The math behind the smear was simple, but the implications weren't. At 90 kilometers per second, 3I/Atlas would cover about 54,000 kilometers in 10 minutes, the same length as the navcam streak. If the exposure lasted the full sequence, the streak fit the model for motion blur, a distant object, moving fast, too faint for a single frame, but visible as a smear when integrated over time. But there was a catch. If the camera had taken a single short exposure, the source would have to be much closer, maybe even in Mars orbit, to produce the same length streak. Without access to the original FITS headers, the exposure time and cadence stayed locked in the rover's logs. Every calculation depended on that missing detail. Was this the comet, or a nearer object flashing through the sky? Lefferland's decision turned a vague rumor into a testable claim. The navcam streak became the first hard number in a sea of speculation, a 54,000 kilometer question mark. For the next round of radio listening and trajectory checks, the math would set the bar for what counted as evidence and what was just noise. A line drawn from Jezero crater on October 7th pointed almost directly toward a spot in the sky famous for one thing: the wow signal. In 1977, a radio telescope at Ohio State picked up a 72-second burst at 1,420 MHz, the hydrogen line. Its source was never found, but the coordinates lingered in SETI lore. Now, with 3I/ATLAS passing within a handful of degrees of that patch, the coincidence was impossible to ignore. Forums filled with back-of-the-envelope math. To match the WOW signal strength from a transmitter 600 astronomical units away, you'd need at least half a gigawatt, maybe 2, if you pointed a dish straight at Earth. That's the output of a major power plant, beamed through the void. Yet, for all the chatter, no public observatory released hydrogen line data from the flyby. No coordinated listening campaign, no raw spectrum dumps, not even a null result. The silence wasn't just optical now, it was radio too. The question hung in the air. With the geometry lined up and the math on the table, why did no one try the simplest test? On October 29th, 3I/Atlas slipped behind the sun from Earth's perspective, vanishing into a glare so intense that even the best telescopes went blind. For nearly 40 hours, no ground-based observatory could track it. The comet's solar elongation, its angle from the sun, shrank below safe limits for all but the most shielded instruments. During this blackout, every theory found room to grow. Some astronomers warned of natural outbursts or a possible breakup, the usual fate for comets under solar stress. Others, scanning orbital models, wondered aloud if a maneuver, something engineered, might be unfolding out of sight. The Galileo project, a team dedicated to searching for signs of non-natural technology, announced a round-the-clock watch on all available radio and optical channels, hoping for any anomaly as the object rounded perihelion. With the main event hidden, the world was left with only models and speculation. When 3I/Atlas reappeared, its brightness, trajectory, and any new fragments would become the next test of both nature's unpredictability and the limits of human surveillance. Early November brings a checklist of tests for 3I/Atlas. Astronomers turned to brightness curves, searching for sudden drops or surges that could signal fragmentation. Orbital models run on new data, checking for tiny deflections, evidence of jets, outgassing, or something stranger. Each measurement is a pass or fail. Does the comet's light fade as expected, or does it split into fragments? Trajectory predictions are checked against reality, looking for any unexplained change. Meanwhile, the JUICE spacecraft waits for its observation window later in the month. Its instruments promise a fresh perspective, but the raw data won't reach Earth until well into 2026. Until then, every shift in the comet's path or brightness becomes a clue, and every delay in the data release keeps the world guessing at what survived the sun. October's sky didn't belong to 3I/Atlas alone. Just days before the comet's Mars flyby, a near-Earth object catalogued as 2025 TF skimmed past Earth, slipping inside the orbits of GPS satellites without warning. The asteroid, only a few meters wide, evaded every major survey until it was nearly overhead. A reminder that even in an era of all-sky monitoring, small and fast can still mean invisible. Meanwhile, two comets set their own unpredictable courses. C/2025 A6, Lemon, began to brighten. Weeks ahead of schedule, hinting at a possible outburst. C/2025 R2 SWAN drew attention for a close approach, just 0.26 astronomical units from Earth, raising hopes for a visible tail and fears of sudden fragmentation. Each event underscored the limits of current surveillance, where the next surprise could come from any direction at any scale. The lesson: the cosmos is full of close calls, and our watch is never complete. On October 7th and 8th, 2025, the European Space Agency released the first official images of 3I/Atlas, just a single blurred pixel, sparking global debate and calls for transparency. The low detail was a result of CASIS's technical limits, not deliberate suppression. Yet the simultaneous silence from HiRISE, Tianwen-1, and HOPE left key data gaps unexplained. Despite viral amateur images and persistent rumors of unusual emissions or precision maneuvers, no official evidence has confirmed these claims. The Perseverance navigation camera streak matched the expected motion blur for an object traveling 90 kilometers per second, but alternative explanations could not be fully ruled out. As 3I/Atlas vanished behind the Sun at perihelion, observers turned to early November for signs of fragmentation or trajectory shifts. The delayed JUICE observations and the recent close pass of Near-Earth Object 2025 T/F underscore the continuing challenges in monitoring fast, unpredictable visitors. To date, the true nature of 3I/Atlas remains unsolved, highlighting both the limits and the urgency of open data in planetary science.